Bismillahirrahmanirrahim. This is lecture number 29. In our previous lecture, we have derived the dispersion relation for an isotropic plate. That we have a waveguide like a plate, and then we have the material of isotropic, that we have isotropic material, and then we have so when we have isotropic material, then we have used the equation of motion for isotropic and stress strain equation for isotropic material, and with the help of boundary conditions we have derived our dispersion relation, symmetric and antisymmetric. We have studied two types of dispersion relations, antisymmetric and symmetric. I have done all the calculation for the isotropic plate, for the symmetric mode, symmetric dispersion relation, except something I have left for you at the end of the dispersion relation, and I have asked you to derive the antisymmetric dispersion relation for isotropic plate. So I did a mistake by writing an extra constant mu on the right hand side of the dispersion relation at the end page of last lecture. That I have written two dispersion relations, symmetric and antisymmetric, at the last page. I think page number this is page number, this is page number 76. So it would be, this would be page number 75. So that page was 74. So on the at the 74 I have written both dispersion relations, symmetric and antisymmetric, and I did a mistake by writing the dispersion relation, and I have written there a constant, extra constant mu on the right hand side of the dispersion relation. So remove that mu from there, and if you did the homework, then you must have found that mistake. But let's see in today's lecture that whether you have found or not. If you did the homework, then you must tell me that you have found this type of mistake. Let's see. Okay, no, today we will discuss analysis of the Lamb mode spectrum. That we will study the analysis of the Lamb mode spectrum. That we have derived the dispersion relation and the dispersion curves corresponding to that dispersion relation are called Lamb modes, and the whole curves are called Lamb mode spectrum, Rayleigh Lamb mode spectrum. So we will see that how can we have those type of dispersion curves, what are their properties, something like that. As we know that when you see the dispersion relation, there are two unknowns, k, wave number k, and phase velocity c. Except than this, nothing is an unknown, because you have CL and CT, and CL and CT are given for the particular material, the material which will be used. Value of CL and CT will be given for that. So it means that you have to make the curves between C and K, phase velocity and wave number K. So with the help of MATLAB, we will plot the dispersion curves, and these dispersion curves are the Lamb mode spectrums. So as we have trigonometric functions in the dispersion relation, so we have infinitely many dispersion curves. So for each value of k, we will have infinitely many values of I should write here C. Mistakenly why I written this thing. This is C. This is C. Then the dispersion relation. So for each value of each k we have infinite values of w, not w for frequency. We will use this omega for frequency, but no, here we have c, small c, phase velocity, because in the dispersion relation you can see that there is k and c. H, what is H? H is basically the thickness of the plate. That is known thing. And k is the wave number and c is the velocity, phase velocity of the wave. So when we plot the dispersion relation, dispersion curve with the help of the dispersion relation, either symmetric or anti-symmetric, we have, with the help of MATLAB, we have this type of curves. So we have infinitely many curves, because along x-axis we will take the wave number k, and along y-axis we will take the phase velocity c. And here I have written normalized wave number. So h and k, this number, this hk is normalized. Why normalized? Means that it has no dimension. How? You know that this h, and this is the dimension of length, and k, and you know that the k is the wave number, that number of waves per unit distance. So it means that dimension of k is the reciprocal of the dimension of h. So both dimensions will be cancelled out, and this would be dimensionless, like here c, and this is also velocity and this is also velocity. C is the general as unknown velocity c, and ct is the velocity of the transverse wave. So when you will have this type of number c by ct, so this would be dimensionless. So it is easy to deal with the dimensionless thing as compared to dimensions thing, dimensions thing, that things have dimensions. Things means that variables have dimensions. I should use the word variable instead of things. That is not good. So here we have this plane, what is with plane KC, K along x-axis and C along y-axis. Normalized wave number, normalized phase velocity, slope of each mode. These curves are called modes. Slope of each mode, what is written here, is negative throughout the whole domain. What does this mean? That when you plot the dispersion curve with the help of MATLAB using the dispersion relations, then you have in this domain, in this plane C and K, along y-axis C, along x-axis K, then all the modes have negative slope throughout the whole domain. That it starts from here and ends somewhere here when this is very large, where wave number is very large. At the start it has negative and negative up to ends it will have negative slope. That is d. What is slope? dc by dk, dc dk, as y and x, and we have dy by dx. So here y is c and x is k, so dc by dk slope, which is negative throughout the whole domain in this plane. I have written here that from inception to end slope is negative. Figure 1 corresponds to symmetric Lamb mode, and one thing is that I have used a symmetric dispersion relation. So these are symmetric Lamb modes. For anti-symmetric Lamb modes, only one thing is different, that the first mode comes from below. All other modes will come from above, and first mode will come from below. Keep in mind that here is 0. Nothing is negative. Not C, not K. Here is we have negative. 0. Plus and plus. Keep this thing in mind. is figure 2 and this is figure 3, figure 2.1 and 2.2. I have written something here on this page for 2.1 and 2.2. Let's see what we have written here. By using figure 2.1, we can see that a region where slope of modes approaches to 0, this region corresponds when C approaches to CL. This region is called plateau region. Spelling, I think it is wrong. P-L-A-T-E-A-U. It should be P-L-A. This E should be here. Plateau. So practice spelling. In the Lamb mode spectrum. So when we have Lamb mode spectrum, so we have different types of thing. That for, like I have told here that we have a plateau region in the spectrum. Let's see 2.1. I have extracted these 2 pages for you people from thesis. No, what is written here? C is plotted as function of wave number. C along Y, K along x-axis. The spectrum appears as in figure 2.1. Now, so this is the figure which I have made with the help of MATLAB. So these are the modes. You can, if you want to count these, then you will have infinitely many modes. This mode we see S0 because these are symmetric. So for the symmetric we use capital S. S0 means S subscript 0, first 0th mode. This is S1, this is S2, 3, 4, 5, 6, 7. So 8, 9, 10 up to infinity. That you will have infinitely many modes. And you can see that in this region, slope of the modes going to 0, that it seems that this slope is 0. This region is called plateau region in the spectrum. And this always corresponds to the value of C equals to CL. What is CL here? As we are using symmetric Lamb modes on a steel plate when kappa is 1.83, showing phase velocity as a function of dimensionless wave number. So we have isotropic steel plate. Value of CL and CL would be given in the literature, and with the help of those CL and CT we have kappa. What is kappa for this? Kappa is 1.83. Kappa will come with the help of kappa is equal to CL and CL by CT. That when you will divide CL with CT you will have kappa. So this value will correspond to kappa. I have said that when C approaches to CL, you have plateau region. When C approaches to CL, you have plateau region. If you normalize both C's, C by CT and CL by CT, follow me at this point. C approaches to CL, and if you normalize C by CT, it means that C by CT approaches to CL by CT. You have to divide both things, C by CT and on right side CL by CT. And CL, what is CL by CT? CL by CT is basically kappa, material constant. So it means that by seeing plateau region corresponding to C approaches to CL, we mean that plateau region corresponding to C by CT approaches to CL by CT, which is kappa. That plateau region will correspond to C by CL, C by CT, C by CT to kappa. That when your C by CT approaches kappa, you will have plateau region in the spectrum. Now, what is value of kappa? Value of kappa is 1.83. You can see that this value is approximately 1.83. This is 1.5 and this is 2. So 1.83 would be somewhere here. So when your C approaches to this value, you will have a plateau region. So this is the plateau region. Let's see what we have written more for 2.1. This region is called plateau region. I have told you correct the spelling PLATEAU in the Lamb modes spectrum. Also, when wave number is very large, all the modes approaches to CT. When we normalize C by CT, then line CT correspond to 1, with that is C by CT is equal to 1, as shown in the figure. It would be 2.1 that we are talking about. 2.1. What we said in the paragraph, that when wave number is very large, then we have with this x-axis, when we are at the very large at this x-axis, then AK is very large, then all the modes, these are the modes coming from above, approach this line, approach this line. When we have large wave number, these modes will approach this line except the last mode, first mode. Only first mode will come below this line. These all modes will approach this line. No, here it is approaching 1. Why it is approaching 1? In the paragraph I have said that C approaches to CT, that all the modes will approach to CT, but here you can see that these are approaching to 1. Why? Because I have normalized this C with CT, that C approaches to CT, and when you will normalize, then it means that C by CT approaches to 1. So that is why all the modes are approaching to 1. And only one mode will cross this line. Here what I was saying for the figure is written here. When C is less than CT, less than CL, the only one mode will cross the line and approaches to CR, Rayleigh wave speed, as shown in the figure 2.2. When we are below the one, that this only one mode will cross this line and approach to the value of CR, which is the Rayleigh wave speed. We will show this, that when our C is less than CT, less than CL, we have Rayleigh wave equation from the dispersion relation. We will show this analytically, but I am telling you only that only one mode will cross this line, and which then it approaches to CR, Rayleigh wave speed. Let's go to the figure 2.2. In figure 2.2 we have used omega c, plane omega c. What does this mean? That on x-axis we have frequency, and along y-axis we have phase velocity. That we will plot c as a function of omega frequency. In figure 1 we have plotted 2.1, we have plotted c as a function of k. Here we will plot c as a function of omega. In this plane, when we plot the dispersion curves, we have two things. One thing is that mode starts with negative slope and ends with negative slope. In general, we have two things. Then one thing is that modes will start with negative slopes and end with negative slopes. What does this mean? Let's see here in 2.2. In 2.2, what we did to investigate, then I will define this word. To investigate the behavior of the Lamb mode, we plot C as a function of frequency, as I was saying. The spectrum appears in this figure. It shows the symmetric Lamb modes for a steel plate. These are the values of CT and CL for the steel plate, as I was telling you. That value, don't know, divide CL by CT, you will have a 1.83. Where I was saying that first thing is that the mode starts with negative slope and ends with negative slope. For example, this mode, its slope is negative. If you check, then till the end it will have negative slope. Now these are approaching to CT. Till end it will have negative slope. But one more thing appears in this domain. What is that? Second thing is an interesting one. You can see that some modes starts with positive slope and end with negative slope. These types of modes are called anomalous modes. That these types of modes have anomalous behavior. Now that's 2.2. For example, this mode, if you check it carefully, then its slope here is positive, then it will go like this, and after this it will have negative slope till the end. So before, when it starts, it has negative positive, and when it ends it will have positive slope and negative slope, positive to negative. So these types of modes are called anomalous mode, and this behavior of modes are called anomalous behavior. So to check the anomalous behavior, we will have to plot C as a function of frequency, not as a function of wave number. When you plot C as a function of wave number, then you will always have normal behavior. That modes always will start with negative slope and ends with negative slope. But to check the anomalous behavior, if the anomalous behavior exists, then some of the modes must, or at least one mode must start with positive slope and end with negative slope. Then slope must be changed. This is one turning point, and if it has two turning points, then it will start from the negative, then positive, then again negative. So that is also normal behavior. Anomalous behavior. In figure, I have also written here something. In figure 2.2, this is for anomalous behavior. In figure 2.2, the shape of the S1 mode is different from the other modes. Then you can see in the figure. It has turning point at this point, 2.686, like here. 2.686 somewhere here. And phase velocity is double valued in this domain. In this domain, from here to here, it would be like here. So phase velocity is double valued for this K, this frequency value. This is called the anomalous behavior mode. So the mode has a zero group velocity. I will define this thing, zero group velocity. Then you will understand this line, this end lines. Now in the following figure, what we did? Now we are moving towards zero group. In the following figure 2.3, we have plotted W as a function of frequency as a function of wave number. So we have three types of plane. When we plot C as function of K, then we always have normal modes, no anomalous behavior. And when we plot C as function of frequency, then we can have normal behavior. This is not necessary that we have normal behavior, but there is chance that we can have anomalous behavior. It is not necessary when we plot C as a function of omega that we have anomalous behavior, but we can have anomalous behavior in that domain. But when you will plot C as a function of wave number, that you cannot have the anomalous behavior, that you cannot know. If the anomalous behavior exists, then even by plotting the C as a function of K, you can't understand the anomalous behavior, that the mode will not show the anomalous behavior. To check the anomalous behavior, as I have written for 2.2, you have to plot C as a function of frequency. Then the anomalous behavior will appear if it exists. Also, third plane is when we plot W as a function of K, so omega as a function of K, frequency as a function of wave number. When we plot frequency as a function of wave number, then curves appear like this. This is S1. This is S1 mode, which is in 2.2. I have written here. This is S1 lamb mode of figure 2.2. This is figure 2.3. And this is S1 mode from figure 2.2, and you can see that from figure 2.2, S1 is anomalous in the sense that its slope dc by d omega changes sign from positive to negative. S1 changes sign from positive to negative, anomalous in the sense. Changes sign that first it has positive, then at the end it will have negative. So changes sign from positive to negative, then we are saying that it is anomalous. So when this S1 mode is plotted in this domain, then we can see that it changes sign from positive to negative to positive. In CW plane, S1 changes sign from positive to negative, but in this plane omega k, it changes to negative to positive, and going through this 0. Here is slope is 0, that if you calculate the slope of this curve, it would be d omega by dk. Here d omega by dk is negative, here it is positive, and here it will be 0. D omega by dk is 0. So slope is 0 here, going through 0 from negative to positive through 0. I have written here. And when you see the S1 in mode in above figure 2.3, its slope d omega by dk changes from negative to positive, passing through 0. So it means that d omega by dk is 0 somewhere here. For that particular domain which is anomalous, d omega by dk must be 0 somewhere in the domain, and we define this d omega by dk as group velocity Cg. We define this d omega by dk as the group velocity. So it means that for an anomalous mode, so what does this mean? In anomalous mode, we have seen that slope changes in C omega plane from positive to negative, and for that most particular mode S1, we have plotted this mode in 2.3 in plane omega and k. In this domain, it changes sign from negative to positive through 0, and this is 0 somewhere. So it means that at the point it is 0, this point is called 0 group velocity point. So a mode is anomalous. It means that for an anomalous mode, Cg is 0. That if mode is anomalous, then its group velocity must be 0 somewhere in the domain. So this we can say this mode as 0 group velocity mode. 0 group velocity mode. This point at which it is 0, it is called 0 group velocity point, and the mode is called 0 group velocity mode, ZGV. Group velocity, as it is from its name, group velocity, you can have its definition from somewhere from the literature. Group velocity, for example, this is example maybe not related with the waves, but if you suppose that you have a ball, empty ball instead, and you have some stones inside the ball, and if you throw the balls from one place to another place, it means that ball will move from start to end, and the stones inside the balls, they will have a velocity, but their velocity is individual velocity, and as a whole, when ball moves, their velocity is called the group velocity. This is this example for understanding, not related particular for this lecture, for this wave, for this topic. This is only for the understanding of the word group velocity. Here I have written for 2.3 group velocity. The mode which is anomalous, this mode has a zero group velocity point, as I have shown you in 2.3, that there is a point in the frequency domain of the mode at which this group velocity is zero. See, GR group velocity, CGR group velocity, d omega by t is zero. This is something extra written. The aforementioned feature S1 mode always exists in all isotopic materials. That we have written that for all isotopic materials, almost all S1 mode is anomalous. And for this type of isotopic material, we have infinitely many anomalous modes. So you can have more than one zero group velocity point. That if the shape of the mode appears like this, then it means that you will have three points, 1, 2, and at 3 points d omega by d is 0, which means that this particular mode has 3 zero group velocity points. It can have 2, 4, 5, whatever. So we conclude that a mode with negative slope dc by d omega in c omega plane phase velocity frequency has positive slope in omega k frequency and k. This is the start part of S1 and it has positive slope up to here. No, this start part of the same mode S1 for in this plane is this. It is started from here and up to here. So it starts from here up to here. It has negative slope, then 0, then positive. In the start it has negative in this plane, and in figure 2.2 where plane is CW, in the start it has positive slope, and after that in 2.2 this mode has negative slope, but after this in this plane this mode has positive slope. So slope is different in both planes. This is I have written here that a mode with negative slope in this has positive slope in omega k. Thank you so much. This is about the Lamb mode spectrums. We will discuss something about the analysis of the dispersion relation in the next lecture, inshallah. Thank you so much. Allah Hafiz.